This is Physics 1060, Descriptive Astronomy. This is Lecture 12.1. Today we're going to be talking about Chapter 12. So we're going to consider here the evolution of stars after they have been on the main sequence, before we deal with how they're formed. Much of our understanding of stars comes from making computer models of how a large mass of gas of typical composition behaves under gravity. It's found that all the main sequence stars are turning hydrogen into helium in their cores. The mass is what determines where on the main sequence a star is. Once a star of a given mass starts, it will more or less stay in the same place on the main sequence for a very long time. The luminosity and temperature of the star do not change much as the fraction of helium in the core increases. Eventually, however, there's going to be a shortage of fresh hydrogen in the core of the star. For our Sun, that time is about 10 billion years. For other stars, we can make use of the fact that the mass of a star is a measure of the total amount of fuel it has, and luminosity is a measure of the rate at which the star is consuming fuel. If we consider both these things, then, we see that the lifetime of a star is proportional to its mass divided by its luminosity. And since we know luminosity is equal to mass cubed, we know then that the lifetime of a star is proportional to 1 over the mass squared. The high-mass stars, therefore, have the shortest lifetimes. An O5 star might have a mass 40 times that of the Sun. That means its luminosity is going to be 400,000 times that of the Sun. In other words, it's 400,000 times brighter, or uses 400,000 times more energy per second. Even though it's a much bigger star, it's burning at such a faster rate that it's only going to last about 1 million years. Whereas a G-type star, say just a little bit above the mass of our Sun, so luminosity almost the same as the Sun, is going to last about 8 billion years. And a low-mass star, say an M star that's only got a half a solar mass, it's only 8% as bright as the Sun, but it will last, theoretically, 56 billion years. Now, stars evolve very slowly, so that generally we can study each star only at one stage in its life. We rarely see stars change, although later we're going to see that stars sometimes undergo a very sudden change at the end of their lives. We usually have no way of knowing how old a star is. Typically, all we know is its luminosity, temperature, and if we're lucky, its mass. We can suspect that a star can change its position on the HR diagram as it gets older, and changes its composition, but we can't immediately tell which stars are older versions of others. For an astronomer, it's a bit like an archaeologist trying to piece together relics as a sequence of time. Since we cannot see inside stars to see what's going on, what we try to produce is theoretical stars that have the same properties of the observed ones, and this needs computers. Astronomers start with a ball of hydrogen and calculate how things like temperature and pressure at different positions inside a star change as thermonuclear reactions take place. In a star like the Sun, hydrogen fusion lasts for 10 billion years. The Sun stays on the main sequence, but it slowly increases in size and luminosity over that time. Now, the change is so slow that life on Earth is not affected by any of these changes. In about another 5.5 billion years or so, there's going to be so much helium ash in our Sun that no more hydrogen burning can take place. When that happens, there's no more pressure pushing out, so gravity starts to win, and the center collapses, and as it collapses and pushes together, the ideal gas law tells us it's going to get hotter. And as it gets hotter, the helium now starts to be converted by another nuclear chain, and that reaction makes carbon. Essentially, 3 helium nuclei go into 1 carbon nucleus. This reaction takes place very quickly, gives off a lot of energy, so that the luminosity of the Sun will increase comparatively rapidly. That extra heat causes the Sun to expand to a much larger radius, and it becomes a red giant star. So this picture here shows, we haven't talked about what a protostar is. It's a star that's being born, and it becomes a main sequence star, and it stays there for a long time. And a star like our Sun as it's burning helium, will become a red giant. Now, in its red giant phase, the Sun is actually going to be larger than the orbit of Mercury. So Mercury would fall into the Sun. And it's going to look enormous in the sky, 50 degrees of angle across the sky. The temperature of the Earth would get so high that life would certainly be extinguished. Red giant stars tend to have very strong stellar winds, blowing a lot of gas back into the interstellar medium. In fact, mass loss is a major feature of the late stages of a star's life. Some stars in these late stages become variable. The balance between pressure and gravity is no longer stable. They grow and shrink with periods ranging from days to maybe many years. As the stars grow and shrink, they can change their surface temperatures, and therefore they move around on the HR diagram. Now, two important groups of variable or pulsating stars here are our Lyrae, which was first discovered in the constellation Lyra, and that has a mass comparable with the Sun's but 40 times the luminosity, and have periods of about half a day. And when we were talking about variable stars before, we mentioned the Cepheid variables, first discovered in the constellation Cepheus. More massive than the Sun, about 20,000 times more luminous, so we can see them from further away. They have periods from 1 to maybe 70 days. The Mira variable stars are pulsating red giants, and the ZC Ceti are pulsating white dwarfs. What I want you to understand is they are variable stars. There's different types, and different types, the period that they vary is going to change. Why do they change? Giant stars pulsate because their atmospheres trap some of their radiated energy. That heats the atmosphere, which then expands, and as soon as it expands, it allows all that radiation to escape. That expanding atmosphere also cools, and so once the radiation escapes and it cools, it shrinks back down and to begin the process again. The higher opacity, the ability to trap radiation, of a star's atmosphere only occurs in a limited instability strip on the HR diagram. Now, many pulsating stars obey a law that relates their luminosity to the period of pulsation. The longer the period, the more luminous the stars. And the reason is larger stars are more massive and have less surface gravity. And so, if I look at a graph then of Cepheid variable stars, and I plot all of them, I notice that they lie on this line. This is a logarithmic scale. You really don't need to understand it. Just know then that there's a relationship between the pulsation period and the luminosity. This is very crucial because it allows me to measure with a stopwatch the time it takes to pulse. And once I know that, then I know its luminosity, therefore its distance exactly. Now, eventually stars run out of ways of generating energy by thermonuclear fusion. The final state of a star depends critically on their mass. We can summarize it with this figure. Here we have the main sequence stars. Red dwarf stars, we're going to see, are just going to kind of fade away and become white dwarfs. We'll talk about what a white dwarf is in a second. Ones about like our Sun are going to be going to their giant phase, and they're going to pulse for a little bit, and then they eventually go down and become white dwarfs. The massive stars become the supergiants, and eventually they're going to end in a supernova explosion. So let's start with medium mass stars. A medium mass star ends its life by ejecting a large fraction of itself back into space and forms something called a planetary nebula. Now, these have nothing to do with planets. The name comes because some of the first to be found in the 19th century looked a bit like images of Uranus. Now, a modern photograph shows a lot more detail. We have the remnant of the star in the center and this expanding ball of gas that's lit, and we can see it due to the UV radiation from the thing in the center. So that star in the center that's left behind is essentially the core of the red giant star that made the nebula. It is very small and very hot, and is in a totally different part of the HR diagram. The central star of the planetary nebula is so hot it gives off lots of ultraviolet radiation that ionizes all the gas around it. The gas is then heated to about 10,000 degrees Kelvin by that ultraviolet radiation. And it has an emission line spectra. Eventually the gas drifts away from the star and becomes part of the interstellar medium, forming new stars. The central star of the planetary nebula has some very unusual properties. It's called a white dwarf. So how do we get white dwarfs? We have a low-mass star like the Sun. It's burning hydrogen. It expands into red giant as the hydrogen and then helium is used up. And the outer layers are driven off by this radiation pressure. The outer layers become a planetary nebula, which is just a shell of expanding gas that dissipates, leaving the core star. So with no fuel available for it to burn, the core star cools, becomes a white dwarf. White dwarf stars have masses like that of the Sun, but sizes like that of the Earth. The density of a white dwarf star is equivalent to 1 ton per teaspoon. Because it's so dense and so massive and so small, the surface gravity is about 100,000 times that of the Earth. It would take as much energy to climb 4 inches high on a solar mass white dwarf as it takes to climb from sea level to the top of Mount Everest on Earth. Now the matter in a white dwarf star is not like ordinary matter. It's not solids, liquids, or gases. In fact, there's no pressure in the normal sense. The star is held up by something called degeneracy pressure, which is something you can only understand from quantum mechanics. White dwarf stars are in hydrostatic equilibrium. Gravity is now balanced by electron degeneracy. Essentially, I can't get the electrons too close together. Degeneracy allows the white dwarfs to shrink with increasing mass. A white dwarf's mass cannot exceed a certain limit, called the Chandrasekhar limit. If it does, it collapses. And the white dwarf's high density, about 1,000,000 grams per cubic centimeter, implies that atoms are separated by distances less than the normal radius of electron's orbit in an atom. The basis of degeneracy pressure is something called the exclusion principle. It's just a law of physics that limits the number of electrons that can occupy any given volume. Degeneracy pressure depends only on gas density, not temperature. When a degenerate gas is compressed, it heats up, but this temperature increase does not affect pressure. In other words, degenerate gases are less springy. Adding mass to a degenerate white dwarf makes it shrink and increases the gas pressure to offset the increased gravity. So again, a white dwarf, if I add mass, it doesn't get bigger, it actually shrinks. Continually adding mass will eventually make the white star collapse. The point of maximum mass for collapse is called the Chandrasekhar limit, and it's a value of 1.4 solar masses. All observations of white dwarf stars' masses appear to conform to the 1.4 solar mass limit or smaller. Now, white dwarfs can introduce a gravitational redshift in their spectra. Photons climbing out of the gravitational field must expend energy to do so. And photons can't change their speed, so it increases their wavelength. The amount of redshift depends on the white dwarf star's mass and radius. Knowing a white dwarf's radius from its luminosity and temperature, the gravitational redshift will give exactly the white dwarf's mass. Mass determination via the gravitational redshift provides a means to determine a white dwarf's mass in isolation. In other words, I don't have to have a binary pair to measure the mass of a white dwarf star. Now, but what if a white dwarf was in a binary system? There, a white dwarf may gravitationally capture gas expelled from its companion. Remember, any star has a solar wind, it gives off material, and that material going in this direction is going to be sucked in and going to spiral down into the white dwarf. So hydrogen is compressed and heated on the surface of this white dwarf. That gas gets warmer and warmer and warmer, and eventually it reaches ignition. A fusion reaction in a degenerate gas results in an explosion, and we call that a nova. Novas can be visible to the eye and may occur repeatedly for the same white dwarf. That explosion does not destroy the white dwarf, as long as the white dwarf never exceeds the Chandrasekhar limit. And what about low-mass stars? Stars with a mass less than 0.4 solar masses are too small to ever ignite helium. When they die, they simply fade away as red dwarfs. When the nuclear reactions stop, the pressure inside decreases, they collapse and they become smaller. The collapse heats them up, so they quietly become white dwarfs in the same way the Sun will. They can have theoretical lifetimes, though, of 100 billion years. That's longer than the age of the universe. So, we really can't see the results of any stars of this size reaching that age. Brings us to the high-mass stars. They have the most interesting deaths. In high-mass stars, things don't stop with the formation of carbon in the fusion chain. Other thermonuclear reactions can take place to make even more complicated atoms. Among the important reactions are carbon going into oxygen and oxygen turning into silicon. These reactions take place much more quickly the larger the atoms. Many of the most common elements heavier than hydrogen and helium are formed this way. The insides of high-mass supergiant stars are the only places we know of in the universe where these atoms can be made in substantial quantities. Later in the course, we're going to learn that when the universe was formed, it first contained only hydrogen. Helium was formed in the first few minutes of the universe, but only a negligible quantity of any other element was formed at that time. The carbon that our bodies are made out of and the oxygen that we breathe were all made inside stars that existed before the solar system was formed. These atoms were blown out into space from the stars and collected again to make a new cloud that formed our solar system. We can tell which elements can be formed inside red giant stars by looking at the physics of nuclear fusion. Now this graph shows how much energy is contained in atoms of different atomic numbers. If we move down the graph, energy is given out. So therefore, we get energy when we go from hydrogen to helium, and from helium down to carbon, and all the other elements. But if you go to an element of mass 80 to an element of mass, say, 40, we need energy, so we can't do that. It takes energy put into the system to do that. Therefore, we can make all the elements simpler than iron in the center of a red giant star, but nothing more complicated on this side. There's a curious relationship between the radius and the mass of a white dwarf star. The more mass it has, the smaller it is. When it gets to a mass of 1.4 solar masses, the white dwarf has 0 radius, which effectively says it can't be a white dwarf anymore. If I were to plot, this is the radius over the radius of the Sun, and as we get down here and we look at its mass, when we get down to 1.4, the radius goes to 0. That limit is called the Chandrasekhar limit. If the core of a star tries to form a white dwarf with a mass greater than this limit, it keeps collapsing to ever smaller sizes, giving off enormous amounts of energy. Because of Newton's law of gravitation, the smaller something gets, the more energy it gives out. So the collapse of the core of a high-mass star gives rise to a supernova, which is an extremely powerful explosion of a star when its core collapses. The star brightens by millions of times in a few hours with no warning to astronomers. This only happens in our galaxy a few times a century, and usually in a place we can't see it. There was one in the Magellanic Clouds, which is the nearest small galaxy to the Milky Way galaxy, in 1987. The light from a supernova fades over a period of a year or so. Now, 3 major things happen in a supernova. The outer layers of a star get blown out into space to form a nebula. The Crab Nebula is one of the most famous of these. It's a result of a supernova explosion that was seen by Chinese astronomers in the year 1054. It's a slowly expanding supernova, and it gives off powerful radio waves and X-rays as well. The gas spreads out into space and eventually fades away. Here's a picture of the Crab Nebula. It's essentially just an explosion of gas from this star. Now there's lots of different supernovas. This is another remnant of a supernova called Tycho's remnant, and it's seen in the radio frequency. And this is Cygnus Loop, which is another supernova explosion. Now, so much energy is available from the collapse of the core of a star that for a brief period, measured in thousandths of a second, nuclear reactions can take place that form elements heavier than iron. Elements like gold, silver, lead, iodine, uranium were all formed in the few thousandths of a second during a supernova explosion and blown out into space. All gold comes from a supernova explosion. The core of the star collapses and forms a neutron star, which we'll discuss in just a few minutes. Supernovae are so bright that there are records of supernovas going back thousands of years. These records are very useful to scientists because we can sometimes identify a supernova remnant that is now seen only by radio telescopes with an actual supernova explosion that took place a long time ago. Some of the descriptions of how the light faded are good enough for us to be able to estimate what type of star caused the explosion. The oldest records are from China and Korea. Neutron stars are much smaller than white dwarfs. A typical neutron star is about 6 to 10 miles across, with a mass of several times that of the Sun. The density of a neutron star is 10 to the 8th tons per cubic centimeter. A neutron star is one possible end state of a supernova explosion. Now, it was theoretically derived in the 30s by Walter Bade and Fritz Zwicky, and a neutron star has the following properties: a radius of about 10 kilometers, a mass between 1 solar mass, and a maximum of 2 to 3 solar masses. Because of its small size, neutron stars were thought to be unobservable. The material of a neutron star is similar to the nucleus of an atom. A way of understanding the neutron star is to think of gravity being so strong as to collapse the atoms themselves so that their nuclei combine. They were predicted theoretically in the 30s based on calculations using quantum mechanics. Again, it was originally believed that they were unobservable because of their small size. However, in 1967, another stellar object called a pulsar was discovered. And there's sources of intense radio emission that flash on and off with periods of a few seconds down to a few fractions of a second. A small number are also visible pulsars. Pulsars flash for the same reason a lighthouse flashes. The radio waves are produced in a region of magnetic field that surrounds the neutron star. The fast rotation is another example of the law of conservation of angular momentum. If the Sun, which we know rotates about once a month, collapsed to the size of a neutron star, it would be spinning at a small fraction of a second. The ultimate fate of a neutron star is to slow down and fade away. Now, ordinary pulsing variables obey a period-density relationship, where the period is inversely proportional to the square root of its density. The long periods of the first pulsars were discovered were consistent with them being white dwarfs. Later pulsar discoveries had much shorter periods. The theoretical neutron star was dusted off for consideration, although at first it appeared that neutron stars would pulsate too fast. The key to explaining pulsars turned out to be a rotating neutron star, not a pulsating one. By conservation of angular momentum, an object as big as the Sun with a 1-month rotation period would rotate more than 1,000 times a second if squeezed down to the size of a neutron star. Such a size reduction is exactly what is expected of a collapsing massive star's iron core. A collapsing massive star is expected to retain its magnetic field, endowing the neutron star with an extremely powerful magnetic field. The powerful magnetic field is such that it beams radiation energy in two opposing directions. The beamed radiation together with the rapid spin gives the pulsar its observed characteristics. Like dynamos on Earth, the spin of the neutron star's magnetic field, not necessarily aligned with the physical spin axis, creates an electric field. This electric field is intense and rips particles from the surface and channels them into two narrow beams at the magnetic poles. The charged particles then accelerate to speeds close to that of light, and in doing so produce radio emissions along the polar axes. Visible light and gamma rays may be produced in very young pulsars. Radiation produced in this manner is called non-thermal radiation, or synchrotron radiation. Then the pulsation of a pulsar is a result of one of the radio beams sweeping across the Earth. Just like a lighthouse, the light is always going as it comes around. You only see it on a ship as it goes around. The pulsar is sending material out, but we only see it as it rotates around and the beam is pointing towards Earth. Electric and magnetic fields of a rotating pulsar exert forces on charged particles in its vicinity and speed them up. The charged particles in turn exert a reaction force on the neutron star, so consequently, if the neutron is forcing them out, the neutron stars should slow down with age, and that's exactly what is observed. Now, before we can discuss anything about the next state, black holes, we need to mention Einstein's general theory of relativity. Newton's law of gravitation is not enough to explain our universe. The gist of the theory is that mass curves the space around it, like a ball on a sheet. Imagine that we got the class together and we had a large sheet, and we were all around the edges and we were pulling it as tight as we could. Be nice and flat. If we threw a ball into the center, it's going to cause a dent no matter how hard we're pulling the sheet. And any other object that rolled by is going to fall into that curvature. So objects that are close to each other fall into the curved space. Einstein's theory predicted several things, including the gravitational deflection of light. So Einstein's general theory of relativity gave a mathematical and physical picture of black holes. Gravity is related to the curvature of space. A black hole is a place where the curvature of space is so extreme that a hole forms. The typical analogy is imagine a waterbed with a heavier and heavier object placed on it. The analogy is only approximate, and a mathematical treatment is a little different. But his theory predicted things like the bending of light. And so if light comes very close to, say, our sun, and we have the sun here, and a gravity well of the sun is pretty steep. So during an eclipse, when the sun is not blocking out, we look at a star, and a star may appear to be right here. Its real position could be behind the sun, and the light is curving around, and we see it from Earth, so that stars appear to be in different locations when we're looking close to the sun. In 1919, British astronomer Arthur Eddington used the eclipse of the sun to test this theory. During the eclipse, the stars that were then visible around the sun were actually in different positions in the sky than when that section of the sky was seen 6 months earlier, thus giving validation to Einstein's new theory. So back to the death of stars. Above about 3 solar masses, even neutron stars are unstable. The gravitational force is so strong that no physical force can halt the collapse. Remember, the closer the objects are, the stronger the force. It seems that eventually we get infinite density and zero volume. This is called a singularity. The question is that a paradox? Can you have infinite density? Can you have all the mass of a star in zero size? Well, it may be a problem, but we can never see it. Nature protects itself. They say it puts a band-aid around itself, because a black hole is formed around the singularity, preventing us from ever seeing it. A black hole is a region of space from which light and matter cannot escape, but they can enter it. We can understand this in terms of the idea of escape velocity. We know the stronger the gravitational field around an object, such as a planet, the higher the escape velocity. In a black hole, the gravity is so strong that the escape velocity is greater than the speed of light. The physics of this is actually somewhat more complicated. To understand it properly, you would need to understand Einstein's general theory of relativity. Now, Einstein's theory also predicts strange behavior near a black hole, such as clocks run at different speeds depending on the strength of the gravitational field. In fact, a very accurate clock. If I had two clocks, one at sea level, one, let's say, in Colorado, they're actually going to run at slightly different rates. It's not that one's calibrated wrong, it's just that time moves differently depending on your gravitational field. It's something we can actually measure now. If the sun were to collapse to form a black hole, which it cannot do, it would be a few kilometers across. The Earth, if it collapsed down, would be a centimeter across. But our motion around the sun would not be affected. At large distances from the sun, Newton's laws would still apply. So if we can never get any light from it, how can we detect a black hole? There are probably many black holes in the galaxy, but because they're so dark, we can only detect them if they're in a binary system. The star Cygnus X1 is a prototype of such a star. There is a visible star whose Doppler shifts indicate that it is one of a pair of binary stars. The other is invisible, but has a mass too high to be a white dwarf or neutron star. Also, the companion is too faint to be a main sequence or giant star. So, by process of elimination, it can only be a black hole. The corroborative piece of information is that Cygnus X1 system gives off very powerful X-rays. X-rays are a sign of gas at temperatures of millions of degrees from Wien's law. The likeliest way of producing this emission is an accretion disk around a black hole. So in this binary star system with a black hole that we can't see, as material comes off of the binary star, some of it gets down and it goes into orbit around the black hole, and collisions cause it to slowly spiral in. As it spirals in, it's going faster and faster, its temperature is hotter and hotter, and finally, just before it falls in, some of it gets shot out in jets along the poles of the spin of the black hole, and we see a strong X-ray source as the material falls in. So the black hole is so close to the other star, it sucks gas off it. The gas is rotating as it falls in and goes into a disk where it heats up as it falls into the black hole. It is a paradox that while black holes themselves are infinitely dark, they can indirectly produce an enormous amount of power. Black holes are also found in the nuclei of distant galaxies and may be responsible for the most powerful objects in the universe, quasars. What I'd like you to do at this point is stop watching the video and watch the black holes video, which will give you a much better understanding and a lot better graphics on how black holes work and the science behind them and all the different strange things that are going around them. It's a pretty good video. I think you'll enjoy it.